2.0.0 Ohm's and Kirchhoff's laws. You'll learn to apply Ohm's and Kirchhoff's laws to various types of circuits, use Ohm's law to solve for unknown circuit values, explain Kirchhoff's current and voltage laws, apply Ohm's and Kirchhoff's laws to solve for unknown circuit values. This section builds on the discussion of Ohm's law in NCCER Module 26103. You'll recall from Ohm's law can be used to calculate an unknown circuit value, voltage, current, resistance, when the other two values are known. In addition to reviewing Ohm's law, this section also introduces Kirchhoff's laws. Gustav Kirchhoff was a German physicist. In 1845, he described laws that apply to voltage and current. Kirchhoff's laws provide a simple, practical method for solving unknown values in a circuit. 2.1.0 Ohm's law. 2.1.1 Applying Ohm's law in series circuits. You can apply Ohm's law to an entire series circuit or to the individual parts of the circuit. When you use it on a part of a circuit, the voltage across that part equals the current in that part multiplied by the resistance of that part. So I always call it Big Ohm's law and Little Ohm's law. Let me zoom out just a hair. In this circuit, we have 95 volts impressed across a series circuit with a 20 ohm, a 50 ohm, and a 120 ohm resistor. So let's see, we have 120 and 50 is 170 and 20 is 190. So we have 190 ohms, 95 volts. There's a half an amp going around this circuit. I equals E, 95 volts, divided by R, 190. So that half an amp going through R1, there's going to be a voltage drop of 10 volts. So E1 equals R1 times I1, and I1 is the same as IT because it's a series circuit, so it's a half an amp, it's 0.5. 0.5 times 20 ohms is 10 volts, and 0.5 times 50 ohms is 25 volts, and 0.5 times 120 ohms is 60 volts. So 60 volts and 10 volts is 70 volts, and 25 volts is 95 volts. Your voltage drops must add up to the voltage source. So here's a highlight. It says to find the total current, IT, using Ohm's law. IT equals ET divided by RT. 95 volts divided by 190 ohms equals 0.5 amps. Okay, then they're just manipulating it to find, they're finding the voltage drops across each of the resistors just like we did. 0.5 amps times 20 ohms, 0.5 amps times 50 ohms, 0.5 amps times 120 ohms. And then they show that the 10 volts, 25 volts, and 60 volts add up to 95 volts. Applying Ohm's law in parallel circuits. You'll recall that a parallel circuit is a circuit in which two or more components branch off of the same voltage source. Branches are like their own individual series circuits, but they all connect to the same voltage source, as shown in Figure 12. So, I'll have to zoom out again. Here's a parallel circuit. Total voltage. Here's R1, R2, R3, and each one of these resistors has the same voltage across it. In a parallel circuit, ET equals E1 equals E2 equals E3. So it says the resistors R1, R2, and R3 are in parallel with each other and with the voltage source. Each parallel branch has its own individual current. If a voltmeter is connected across R1, R2, or R3, the voltage drops E1, E2, and E3 will each be equal to the source voltage, ET. Make it bigger so we can read it. So, when the total current leaves the voltage source ET, I1 portion of the total current flows through R1, I2 flows through R2, and I3 flows through R3. The total current is equal to the sum of all the branches. This formula applies for any number of parallel branches, whether the resistances are equal or unequal. Here's a highlight. I1 equals E1 divided by R1 equals ET divided by R1. Because it's parallel, E1 equals ET. Okay. Example number 1, see figure 13. Make it a little smaller. The two branches R1 and R2 draw a total line current of 20 amps across a 110 volt power source. R1 and R2 are in parallel. Branch R1 takes 12 amps. What is the current in I2 in branch R2? Well, we have a couple of different ways to solve this. We could say that 20 minus 12 equals 8, and that would be the current in I2. Well, yeah, I guess that's it. They're not telling us what the values of R1 and R2 are. So if we have 20 amps, actually this is a good introduction to Kirchhoff's current law, because Kirchhoff's current law says that all of the current entering a node must equal the current leaving that node. So 20 amps comes into this node and 12 amps is going through R1. We know that we have 8 amps that has to go somewhere. So it's going through R2. Since we know the total current is equal to the sum of the branch currents, we can rearrange the formula to find I2 and then substitute the given values. So IT equals I1 plus I2. I2 equals the total current minus I1. So 20 amps minus 12 amps equals 8 amps. In figure 14, let me make it smaller. The two branch circuits, R1 and R2, across a 240 volt power source draw a total line current of 35 amps. Branch R2 draws 20 amps. What is the current in I1 in branch R1? Well, 35 minus 20 equals 15, so there's 15 amps flowing through R1. Knowing that we could, well, we know the voltage drop is 240, so we could divide that by 15 and find what the value of R1 is. We could do the same with R2. 240 volts divided by 20 amps equals what? 12 ohms. So R2 is 12 ohms. R1, I didn't do it in my head because it's not an easy number. But 15 amps is what is flowing through I1. So let's go on to 2.1.3, applying Ohm's law in series parallel circuits. Recall that series parallel circuits combine the elements and characteristics of both series and parallel circuits. You can apply the same equations you use for series and parallel circuits to find the values for individual paths in a series parallel circuit. I'll tell you what, let's take a look here. What are they asking us here? Figure 15 shows a simple series parallel circuit with a 1.5 volt battery. Work through the following steps to complete the calculations. So what do they want us to tell them here? I don't know if they want us to show them what the current is, but that's what we'll do. Oh, they want to know what the total, yeah. All right, well, let's do this one then. Let's go to the 3DBB and we'll copy this. I kind of wish I could copy this and paste it, but I have to draw it by hand. So 0.5 kiloohms, 0.5 kiloohms, 1 kiloohm, 1 kiloohm. All right. These are going to be pretty small currents, to say the least. We have 1.5 volts, and we're putting into 500, 500, and 1,000 and 1,000 ohms. So it's going to be a small current. That's all right. We won't let that bother us. Let's turn the page here, and we'll draw this. Oops, wrong color. Come here. Let me get my color here. And we'll find the circuit values. Here's my battery, and we're going to go through two series resistors. And then we're going to go through, wow, that's a horrible drawing, but you can forgive me there. We'll go through two parallel resistors. Make sure that our drawing looks basically the same as their drawing. We have 1.5 volts, if I remember correctly, and this is 0.5 kiloohms, and this one is 0.5 kiloohms. This one is 1.0 kiloohms, and this one is 1.0 kiloohms. Let me see if that's right. Yes. Oops. Where? Oh, come on. There. 0.5, 0.5, 1, and 1. Okay. Very good. 1, 2, 3, 4. All righty. So this is R1, R2, R3, and R4. So we're going to combine R3 and R4. We have 1,000 ohms and 1,000 ohms. If it's easier for you to convert to ohms, go ahead and do that. If you want to leave it as kiloohms, you can do that too. So 1 kiloohm and 1 kiloohm, they're the same value. So we're going to say 1 divided by 2. I'm going to make an equivalent resistor here of 0.5 kiloohms or 500 ohms. So now I have an equivalent circuit. Let me see if I can do this real quick. We've got an equivalent circuit of 1, 2, 3, and I'm going to leave that one. My board is a little bit off kilter here. There we go. I'm going to make this one orange because it's an equivalent resistor. This is R34, and it's 0.5 kiloohms. And this is R1. This is R2, and they're both 0.5 kiloohms. And now everything is in series, so what we'll do is we'll add all of our resistors together, and we'll get 1.5 kiloohms, or 1,500 ohms. So my RT equals 1.5 kiloohms, and my voltage is 1.5 volts. So if I wanted to know the total current now, we have to be careful here. We have to be careful. Oops, wrong color. How did I get that green? E total divided by R total equals our current total, I total. So substituting the values that we know, if we have 1.5 volts divided by, now this is where I'm going to confuse us, 1.5 kiloohms equals 1 milliohm. It's 1/1000th of an ohm, because this is actually 1,500. And with our calculator, I'll just check my math, saying 1.5 divided by 1,500 equals 0.001. So it equals 1 milliamp, oops, wrong color, or 1 milliamp, or 0.001 amps. That's our current. So we have 0.001 amps flowing through R1. And we have 0.001 amps flowing through R2. And 0.001 amps flowing through R3. Actually, yeah, R34, excuse me. So if we wanted to find the voltage drops now, we could say E equals I times R. So we have 0.001 times 500. It equals 0.5 volts. 0.5 volts. And this is the same value. It's 0.5 kiloohms times 0.001 amps equals 0.5 volts. And we'll do that on the calculator to make sure that I'm not lying to you. Come on. There. So, 0.001 times 500 equals 0.5. It's a half a volt. So that means that over here on R34, we have 0.5 volts dropped across R34. If we were to go back up to the original circuitry, I will take this equivalent resistor out of the circuit. And there, I'll draw this back so it's not orange anymore. We will find our voltage. We have 0.5 volts dropped across R4, and we have 0.5 volts dropped across R3. So here, 0.5 volts divided by 1,000. Let's try that. 0.5 divided by 1,000 equals 0.0005 amps. And what did we have over here? We had 0.001 amp. We had we had 1 milliamp, 0.001 amps total, 0.001 amps flowing through R2. And now we have 0.0005 and 0.005 amps flowing through R4. If we were to add those two together, 5 10,000ths and 5 10,000ths, we would get 10 10,000ths or 1 1,000th. And that's what our total current was, remember? Equals 0.001 amps, 1 1,000th of an amp. So that current flows through R1, it flows through R2, and then when it gets to this node, it splits at half of it. 5 10,000ths of an amp flows through R3, and the other 5 10,000ths of an amp flows through R4. Right. We could call this 0.5 milliamps. We could call this 0.5 milliamps because milli is 1 1,000th. And this is 1 milliamp, and this is 1 milliamp. I know, I'm writing all over the boards now. I've got us good and confused. I hope you were able to follow that. I hope that helped out a little bit. But let's go back to the book then. Let's see what they have to say. So they did the same thing. They added R1 and 2 and got 1 kilo, 1,000 ohms. And R3, 4, they used the reciprocal method. 0.001 plus 0.001 is 0.002. And then when they reciprocated the last time, they got 500 ohms. That's the equivalent resistor. So here they've drawn an equivalent resistor. R12 is 1,000 ohms, and R34 is 500 ohms. And they ended up with 1,500 ohms, or 1.5 kilohms, when they added everything together. So our voltage is 1.5 volts, and our resistance is 1.5 kilohms, 1,000 ohms. So the current is 0.001 amps, or 1 milliamp. Note the value of 500 ohms can be converted to kiloohms by dividing by 1,000. Therefore, 500 divided by 1,000 is 0.5. So 500 ohms equals 0.5 kiloohms. Okay, step 6, determine the voltage drop across each series resistance by using the total current and the resistor's value and the correct form of Ohm's law. So they did that. They used 1 milliamp times 0.5 kiloohms, and they got 0.5 volts. They did that twice because they're the same values. So R34 also, they have 0.5 volts, but they're parallel, so the current splits off and only half the current goes through each. So it's 0.5 milliamps flowing through each. 2.2.0. Kirchhoff's current voltage laws. German physicist Gustav Kirchhoff developed two laws related to current and voltage in an electrical circuit. These are Kirchhoff's current law and Kirchhoff's voltage law. 2.2.1, Kirchhoff's current law. This is a highlight. It says Kirchhoff's current law states that at any point in a circuit, the total current entering that point must equal the total current leaving that point. They call those nodes. And basically here they're saying they have 5 amps coming in and 3 amps coming in. They have to have 8 amps leaving. Remember that current is actually movement of electrons. So this 8 amps of electrons can't come into this node unless 8 amps of current is leaving that node. It's like an elevator. Only as many people can get on as get off. Currents 1A and 1B, or IA and IB, are positive because they flow into point P. Current IC flows out of point P, and therefore is negative. Kirchhoff's voltage law. This is highlighted. It says Kirchhoff's voltage law states that the algebraic sum of the voltages around any closed path equals 0. So EA equals E1 plus E2 plus E3. EA, I guess, is the supply voltage, or the applied voltage, I think they call it, applied. So here you have 100 volts, and we have 50 volts, and 30 volts, and 20 volts. Notice that that 50 and 30 and 20 add up to be exactly 100. Note, for convenience in labeling, letters, subscripts are shown for voltage sources, and numerical subscripts are used for voltage drops. So EA minus E1 minus E2 minus E3 equals 0, or EA minus the sum of E1 plus E2 plus E3 equals 0. So Kirchhoff's voltage law may be applied using a loop equation. Any closed circuit path for current flow is called a loop. A loop equation specifies the voltage around the loop. Let me make this bigger if I can. Here we go. In its most general form, Kirchhoff's voltage law states that the algebraic sum of all potential differences in a closed loop is equal to 0. A closed loop means any completely closed path consisting of wire, resistors, batteries, or other components. For series circuits, this implies that the sum of the voltage drops around the circuit is equal to the applied voltage. For parallel circuits, this implies that the voltage drops across all branches are equal. Before you write loop equations, you need to develop a convention for deciding whether a component in the loop is a voltage rise or a voltage drop. Do not assume that all sources are rises and all resistors are drops. as this convention can be faulty. Also, it doesn't work if you have a loop with nothing but resistors and no sources. Okay. Let's see if we can take a look at this. I'm not sure why I have two of these. I'm going to get rid of one. There we go. All right. Well, let me just have a quick discussion about Kirchhoff's voltage law. Oh, that's horrible. Hold on. Try that again. Come down. Make my little squiggle. Come over. Make my little squiggle. Here, okay. And what I want to do is assign voltages to this. I'm going to call this 120 volts. I'm going to call this 60 volts and 40 volts and 20 volts. Now, I'm going to go ahead and extend my page because I'm pretty sure I'm going to need it. So let me just extend it now and then we'll come back up. Well, here's what Kirchhoff said. Basically, he said the sum, and this is sigma, it's used for sum of voltage rises minus the sum of voltage drops in a closed loop equals 0. In other words, the rises and the drops must equal each other in a closed loop. Now, let's talk about what's going on inside this loop. We said before that current flows from negative to positive, didn't we? We said that. Current flows from negative to positive. So, going through this resistor, the first side of this resistor is negative, and the second side is positive. Same with resistor R2. The first side is negative, the second side is positive. R3, the first side is negative, and the second side is positive. Now look what happened here. We have negative, positive, negative, positive, negative, positive, positive, negative. The polarity of this battery is opposite to the polarities of these three resistors. Excuse me, these three voltage drops have an opposite polarity: negative, positive, negative, positive, negative, positive. Opposite to the source, positive, negative when you're going in a loop. That's why they cancel out. That's why when you subtract them, you get 0. Suffice it to say that the sum of voltage drops added together equals a voltage source, or applied voltage as they call it. So the sum of the voltage drops equals the applied voltage. But it's more than that. It's the voltage, applied voltage minus those voltage drops because of their polarity being opposite to that voltage source, that we end up with a sum difference of 0. So I hope that actually cleared some things up and didn't just confuse you. But the polarities are opposite through the resistors. The voltage drops are opposite in polarity as the voltage rise. Negative, positive, negative, positive, negative, positive, positive, negative. Okay. Kirchhoff also has a current law, and that current law, boy, why did that happen seasick here. Let's see if that's better. There. This Kirchhoff's current law states that the current entering a node has to equal the sum of the currents leaving that node. So again, he uses that sigma. Sum of currents in equals the sum of currents out. Or you can write it another way where you say sum of the currents in minus the sum of the currents out equals 0. And we can see that if we have 10 amps and 8 amps is leaving to the right, well, that means there's only 2 amps left to be coming down through this branch. Okay. Let's go back to here then. There we go. Oh, come on. There. So, it says if the sign is positive, treat the component as a voltage rise. If the sign is negative, treat the component as a voltage drop. Consider the inside loop through A, C, D, and B in figure 19. So here's A, C, D, and B. This includes the source, ET, and the voltage drops, E1, E2, and E3. So again, there's going to be a polarity. This is the negative, this is the positive. When we come through this resistor, the first half is negative, the second half is positive. Negative, positive, negative, positive. 240 volts, here's 30 volts, 90 volts, and 120 volts. And 30 and 90 is 120, plus 120 is 240, and 240 minus 240 equals 0. There it is right there. I'd like to highlight this, but it's part of a diagram or a figure. So when you click on it, it just shows you the figure. I can't highlight on it. But write the counterclockwise formula. They're saying negative ET plus E3 plus E2 plus E1 equals 0. Substitute the voltage values, negative 240 plus 120 plus 90 plus 30 equals 0. See, I wouldn't have gone counterclockwise with this. I would have gone in the same direction as the current flow. That's the way I always do it. Here, there you go. Here's the clockwise formula. Negative 1, minus 2, minus 3, plus the total voltage source equals 0. Voltages E1, E3, and E2 have a negative value because there is a decrease in voltage seen across each of the resistors in a clockwise direction. The source ET is a positive term because an increase in voltage is seen in that same direction. I'm not going to worry about the counterclockwise. Applying Kirchhoff's voltage law. Let me see if we can see this. There you go. So here's 15 volts, and we're coming around. We have 3 volts and 6 volts. That's 9 volts, plus 2 volts is 11 volts. 15 minus 11 equals 4. So this EB must be 4 volts. 3 volts, 6 volts is 9 volts, and 4 volts is 13 volts. 2 volts is 15 volts. Minus 15 equals 0. So that's what they're saying here. Negative or minus E3 minus EB minus E2 minus E1 plus EA applied voltage equals 0. So EB equals voltage applied voltage minus E3, E2, and E1. So 15 volts minus 2 minus 6 minus 3 leaves 4 volts. Since EB is positive, the assumed direction of current is in fact the actual direction of current. Let's see if they'll give us 2.3.0, applying Ohm's and Kirchhoff's laws. Now we can take everything you've learned thus far and apply it to a circuit. Refer to figure 21. Application of Ohm's and Kirchhoff's laws. So here they have a partial, or it's a series parallel circuit. R1 is in series. R4 and 5 are in series. R4 and 5 are parallel to R3. And R2 is in series with everything else. And look, it shows us that through R2 we have the total current of 6 amps, and through R1 we have the total current of 6 amps. So now we can figure out what we need to know. Let me try to recreate this on the smart board. I know, I'm sorry, this video is going on pretty lengthy, but I hope it's helping. Anyway, okay, this is our circuit. We have 240 volts at the source. We have 5 ohm resistor R1, a 15 ohm resistor R2, a 60 ohm resistor R3, a 10 ohm resistor R4, and a 20 ohm resistor R5. So looking at this circuit, it's a combination series parallel circuit. And we can see that R4 and R5 are in series with each other. When we trace them with our pencil, we don't stop until we go through both R4 and R5. Right here is a node, and right here is a node, so R3 is in parallel with R4, 5. So the first thing we're going to do is combine R4 and 5. And since they're in series, we're going to add them together. R4 plus R5. So 10 ohms plus 20 ohms equals 30 ohms. So let's go. I've taken the liberty of drawing this. Here's my equivalent resistor, R4, 5, and it's 30 ohms. So now we have R3 in parallel with R4, 5. And we want to combine these two. So we could do the reciprocal method, or we could do product over sum. R3 times R4, 5 over R3 plus R4, 5. So that's 60. Well, I'm sorry, let me give myself a little bit more room. Let me come down here. 60 times 30. 60 times 30 over 60 plus 30. That's product over sum. So that's 1,800 divided by 90. And to make it easier on me, I'm going to go ahead and get rid of one of the zeros and say 180 divided by 9, and that equals 20. 9 goes into 18 twice, and then there's an extra 0. So it's 20 ohms. The equivalent resistance has 20 ohms. Let's go to the next page. And here you'll see we have the equivalent resistor of 20 ohms, R3, 4, 5. Now we have a simple series circuit with R1, R3, 4, 5, and R2. So we're going to add those together. R1 plus R2 plus R3, 4, 5. So 5 ohms plus 15 ohms plus 20 ohms equals 40 ohms. 5 and 15 is 20, plus 20 is 40, 40 ohms. So my total resistance is 40 ohms. And we could have figured that out by taking 240 volts divided by 6 amps. So we could have used Ohm's law and found our total resistance to be 40 ohms. Now we have 6 amps flowing through R1 and 6 amps flowing through R2. So we can find our voltage drop by saying E1 equals R1 times I1. And I1 is actually IT. It's 6. So we have 5 ohms times 6 amps. And that equals 30 volts. So we'll put that across R1, 30 volts. Same with this, we have 15 ohms times 6 amps. So that's 90 volts. 90 volts. 90 volts. Just to make sure that I'm not, there we go. Make sure I'm not crazy. I'm going to say 15 times 6 is 90 volts. Okay. Well, now we know we have 30 volts and 90 volts. And here is 20 ohms times 6 amps. So we have 120 volts dropped across R3, 4, 5. 120 volts. That's either 20 ohms times 6 amps equals 120 volts. Or we could have said 240 minus 90 plus 30. 240 minus 120 equals 120. So we have 120 volts dropped across these resistors. Well, R3 and then R4, 5. So let's go back. We have 120 volts dropped across R3, and we have 120 volts dropped across R4, 5. So here we can find the current by saying 120 volts divided by 60 ohms. This is little Ohm's law. That gives us 2 amps. 2 amps. So if I have 2 amps flowing through R3, then I have 6 amps minus 2 amps. I have 4 amps flowing through R4, 5. Oh, that's right. I don't know why that looked. So we have 120 volts divided by 30 ohms. We have 4 amps flowing through R4, 5. That's right. All right. For some reason, it didn't look right to me for a second, but okay, I'm back now. So we have 2 amps flowing through R3. We have 6 amps flowing through R2 and 6 amps flowing through R1. And we already said that we had 30 volts dropped across R1 and 90 volts dropped across R2. So let's go back to the original right here. We have 30 volts and 90 volts. And we had 120 volts and 2 amps. And we had 4 amps going through R4, 5. So we have 4 amps going through R4. And we have 4 amps going through R5. And 4 times 20 ohms is 80 volts. And 4 amps times 10 ohms is 40 volts. And notice how 40 and 80 equals 120. These two parallel branches have the same voltage, 120 across R3 and 120 across R4, 5. So there we go. We know all of our currents. We know all of our voltage drops. We've solved this, and we could even go back and do power if we wanted to, we could use any one of the three power formulas. P equals, P equals, P equals. So this is E times I, E squared over R, and I times R. E times I, P equals E times I. P equals I squared times R. P equals E squared divided by R. Those are our three power formulas. So if we wanted to find out what the power is in all of these, we could say 30 times 6, that's 180 watts. I also could say 6 squared is 36 times 5 is 180 watts. I could say 30 squared, which is 900, divided by 5. Let's see if 900, 900 divided by 5. Does that give us 180? It does. So any one of those three will give us the same wattage because all three of them work. So 40 times 4 is 160 watts. And 80 times 4 is 320 watts. And 120 times 2 is 240 watts. And 90 times 6 is 540 watts. Wow, that's a lot. 540 watts. So I'm going to add all these together. I have 180 and 540 and 240. Bring my page down. And 160 and 320. 160 and 3. Oops, I didn't put my 320. Excuse me. Hold on. 160 and 320. And let's see what we get. That seems like a lot. Let's find out. 8 and 4 is 12, and 4 is 16, and 6 is 22, and 2 is 24. And 2 and 1 is 3, and 5 is 8, and 2 is 10, and 1 is 11, and 3 is 14. 1,440 watts in total. PT equals P1 plus P2 plus P3 plus PN. Now, we said 1,440 watts. Look, we have 240 volts and 6 amps. I don't know if I ever, what was the total, if we went back to this last one, what's the total resistance in this circuit? 20 ohms. The total resistance is 20 ohms. All right, so 240 times 6. Let's see what 240 volts times 6. 240 volts times 6 amps is 1,440 watts. So it seems like that worked. 1,440 watts. And let's see what 240 squared divided by 20. My total resistance was 20 ohms, we said, right? So what is 240 squared, 240 E squared divided by 20 ohms? No, how did I get 2880? I'm sorry, I did something wrong. What did I do wrong? What did I do wrong? What did I get for 240 squared? 57,600 divided by 20 ohms? Yeah, what's wrong? Where am I getting that? Hold on, clear. 240 times 6 is 1440. And 6 squared is 36 times 20. Now, it must be 40. I wrote it down wrong, didn't I? What did I do? What did I do over here? Oh, I'm sorry. I didn't put down my 5 and my 15. We've got a total of 40. That's what I did wrong. I didn't go to that final step and make this 40 ohms. I left it when I cut and spliced. All right, there we go. Well, see, if the math doesn't work, we made a mistake. The math didn't. We've got 40 ohms of total resistance. Very good. I even wrote that right there, 40 ohms. How do you like that? All right, very good. So over here, this is where I made the mistake. We've got 40 ohms. I knew something didn't look right. There we go, 40 ohms, okay. So 240 squared divided by 40 is 1440. So 240 squared divided by 40 is 1440. And 6 squared times 40 is 1440. So however we do it, we get 1,440 watts. When we add all these together, we get 1,440 watts. So everything works. All of the math works. I know. That's very confusing, isn't it? Look at that board. All right. All right, let's go back and finish this section out. I'm dragging my feet here. Okay. All right. So let's see what they have to say here. It says, caution when simplifying information within a circuit, it's important to make sure that all the simplified values remain equivalent to the original values in the circuit. Any errors will result in a faulty final calculation. Well, we just saw that, didn't we? Before you can calculate the current through the circuit, you must calculate the total resistance. To do this, use the formula for resistors in series to find the equivalent resistance for the 2 resistors in the right-hand loop. That was R45, it's 30. And then we use product over sum. They're using the reciprocal method to find the total of 20 ohms. And then that is in series with the 15 and the 5. So we got a total of 40. And then we figured out, because we have 240 volts and 40 ohms, we had 6 amps of total current. Knowing that we have 6 amps, then we should be able to go back and find the voltage drop. 5 ohms times 6 amps is 30 volts. And 15 ohms times 6 amps was 90 volts. So we ended up with 6 amps flowing through R3 and 4 and 5. We have to find out how much we have. Use Ohm's law to find the voltage drops across R1 and R2. So we did the voltage drops and found 30 and 90. Use Kirchhoff's voltage law to find the voltage drop across R3. So when we do it, we got 120 volts. Remember that per Kirchhoff's current law, the current flowing through R1 is the same as the current flowing through R2. Therefore, 6 amps times 5 ohms is 30 volts, and 6 amps times 15 ohms is 90 volts. By using Kirchhoff's voltage law, the voltage drop across R3 can be calculated. 240 minus 30 minus 90, we have 120 volts across R3. We also have 120 volts across R45. So here they're finding out what the current is by taking 120 volts divided by 60 ohms. We have 2 amps. And if we do 6 amps minus 2 amps, we are ended up with 4 amps going through R45. So use Ohm's law to find the current flow through R3, 2 amps. Use Kirchhoff's current law to find the value of I45. 6 amps minus 2 amps equals equals 4 amps. Okay, they said minus I45 equals 0. And they said I45 equals 6 amps minus 2 amps, so it's 4 amps. The total current IT into point C is 6 amps. It then divides into two currents, I3, which is 2 amps, and I45, which are both direct outputs of point C. So it's 4 amps. Now that we know that, we can find out what the voltage drop is across R4 and across R5. So here 4 amps times 10 ohms is 40 volts across R4, and 4 amps times 20 ohms is 80 volts across R5. Finally, check the calculations for this loop by applying Kirchhoff's voltage law around the loop. So we have 120 minus 40 minus 80 equals 0. Very good. All right. 2.0.0 section review. Two branches of a circuit R1 and R2 across a 120 volt power line draw a total line current of 30 amps. Branch R1 takes 15 amps. What is the current I2 in branch R2? Well, 30 minus 15 is 15. So I2 equals 15 amps. B. Who stated that the current entering a point must equal the total current leaving that point? Kirchhoff. Kirchhoff's voltage law can be used to check calculations made using Ohm's law. True. We can use those two laws to check a circuit. Very good. This concludes Module 26104, Electrical Theory. Please like and subscribe. I hope you got something out of it, and I'll see you on the next video. Thank you. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.